Hello and welcome to a new series. In this one, we're going to write a interpreter and compiler for my own little stack-based language in Rust. And we're writing it in Rust because it's been written in C++, which is yucky. And instead, we're going to write it in Rust, which is hip and cool. Okay, it's really important information. So in this video, we're going to get into the old implementation, figure out roughly how it works, what's going on in it. We're going to run it. We're going to talk about the performance. We're going to talk about optimizations. We're going to talk about other things that we could do and we will do in the series, and then we're going to actually start implementing it. I talk a lot in this one, so you can skip to about 18 minutes to get to the implementation of it, but it might still be interesting to figure out what we're actually doing. So that's what the first part is about. Yeah, enjoy the series. Hello and welcome. Today we're going to do something a little bit different. I have my camera on, just because it's a little bit more human. Maybe it's easier to watch like way too much way too many hours of content with a little face in the top right, I think. Though I'm mostly going to be looking down there and up there, so not sure if that's going to be awkward, but we're going to see what happens. Now specifically, today what we're going to do is recreate one of the programs that I've written before. Now I didn't write this one on video, the other one that I'm like re-implementing. I didn't write it on video, and I don't think I made any videos about it. It's about, actually, let me share the screen of this one. Yes, there it is. Okay, so what this is it's called my concise language. It's a completely made up language where you basically just have stack-based instructions. Reads a little bit like an assembly language, and what essentially happens is that these instructions push onto a stack, other instructions take off the stack, and so forth, basically. So that's what that is. And this is a good opportunity to sort of learn a lot about interpreters, about parsing a little bit, not very much. And then also to figure out how do you optimize stuff like this? How do you optimize an interpreter and stuff like that? So we're just gonna get right into it. I'm gonna show you what the current program does. Then we're gonna rewrite it in Rust because that's a meme, and I like memes, so we're gonna do that. To be completely honest, the reason I'm doing this is because it's fun and I want to learn more Rust. I'm not that good at Rust yet. So here's an MCL program that specifically shows a few of the things that it's capable of. So the main thing is arithmetic, right? That's the only thing it's really capable of at the moment, but there's no point in keeping it like that. I mean, it's kind of boring. So adding floating point instructions and adding strings and things like that is definitely going to have to happen at some point, just to make it a little bit less of a toy language, right? Not that this is ever going to be a big thing like Minix, but yeah, all the memes today. We're pulling out all the old memes. So what this program that you're seeing right here specifically does is calculate whether this number is a prime. Now, happens to be a prime, okay? So that's an expensive case, right? Checking whether something is prime has sort of two cases, or three cases, let's say. The first case is that it's obviously not prime, so divisible by 2, let's say. Like an even number, right? So half of all numbers are gonna not be prime, so that's pretty common. And then there's, numbers that are divisible by anything from 0 to 50 or some shit. Like those are pretty easy to spot sometimes, like, like the I don't know, the 80, for example. 80 is not prime, it's pretty simple to spot. But then you run into the third case, which is it is a prime. And disregarding modern methods where you do some sort of probability calculation and things like that to sort of figure out what may be a prime and what may not be a prime, the basic approach is that you have to test whether it's a prime at some point, right? So if you're going to test whether it's a prime, you end up having to walk through a lot more cases if it is prime, right? Because you have to sort of prove it by exhaustion, by exhausting all possible options, right? So you check all possible options, which means that generally what you do for now a large prime number like this is you take the square root of it and you check every number up to that square root of this number, and yeah, you just, you can do some other smart heuristics. You can skip a bunch of multiples of other numbers and things like that. But what this program does is the super stupid approach. Okay, so the super stupid approach is to start at 2 and see if the number is divisible by 2. If not, see if it's divisible by 3, and so on, right? So 4, 5. So this doesn't skip all the even numbers, which is stupid. But let's just disregard the fact that this is a stupid implementation of a prime checking algorithm, which is not what this is about whatsoever. And instead, let's think about the fact that this is written in MCL. And now MCL has been optimized a little bit. This doesn't JIT compile. It doesn't do like AST interpreting. It doesn't do like it doesn't do any of this stuff. It's just a simple bytecode interpreter. It just loops over the bytes and but well, it's a bytecode interpreter at least. It doesn't interpret the fucking strings. It at least goes and compiles it to a bytecode representation first, which gets rid of all the sort of the parts where you have to figure out, oh, is this a number or not, and all that sort of error checking is obviously part of the compilation step, which you can do beforehand. But before I talk for another 30 minutes, let's get into it. Okay, so the first thing that we're going to do is run this program and see how quick it is, just because it's fun, right? So I have it compiled here, the MCL program, which is this version. And MCL is just written in C++. Okay. Actually, can you see my? Yeah, you can see my screen. Okay, cool. Poggers. Next. So what you can do here is you can compile a program and stuff like that. We're gonna just go right into it. If you just run MCL with the program, that was the primes.mcl. Then what happens is it generates the bytecode. It optimizes it, runs a few optimization steps, super simple shit, and then runs the bytecode, okay? So what we see is that it takes a little bit of time, and what it tells us a little bit of things. It does substitution optimization and fault optimization, which is like super basic, so we're not gonna talk about those right now. We're gonna get into that later when we implement them. But we take 23 actual instructions, or abstract, but they're actual instructions, right? They're basically what we saw in the file, and we fold them down into 15 instructions, and these are also like, there's some optimized instructions there and things like that, and that gets written into a bytecode, and the bytecode gets executed. And so the result we see here is 1, which is the result of our primes program, which just means that we have detected that it is a prime. So let me compile this really quick. And then if we look at the primes MCLB, which is the bytecode, it doesn't know what it is. And the reason for that is that this is binary data, okay? And you see it's highly unoptimized for size, because we don't actually care about sizes here. We're fine with using a shitload of hard disk space, because it's a toy language at this point. And these are all constant size instructions, right? So each instruction is 8 bytes, and that's how it works. It's really simple. So now if we run it, we can actually time it, because otherwise we would be timing the compilation step, right? So if we now time this with the time utility, which is like the best way to do it by far, we see that it takes about 1.7 seconds. That sounds about right, yeah. 1.7 seconds, and now if you go and write the same program in Python or something else, it is obviously slower. So this is faster than Python, awesome. Not that hard, I can probably do it in my head faster than Python. No offense to Python programmers, it's just slow. But if you write the same code in C, for example, it absolutely crushes it. Obviously, like there's no way that a bytecode interpreter like this can just crush a C program that does only math, right? There's very little room for sort of optimization in the C program here in terms of actually executing this. Of course, if you write a smarter primes algorithm, of course you can optimize the fuck out of it, right? But specifically in this case, we have about 1.7 seconds to run this program. And once we're done with the Rust implementation, we're going to also do the same test and figure out if it's faster just for fun. But yeah, so let's look at the code really quick. And I promise we're going to get into Rust this episode. Don't worry about it. So there's a bunch of stuff here. I'm going to show the interpreter first of all, right? Because that's the sort of important part. And let me just do some stuff here. Okay, so what happens is we have a stack, right? Remember, stack-based language. And that's this thing. It's just an array, a sort of static array of int64s, right? Because the language currently only supports 64-bit signed integers. Fine, right? We don't care. And then also we keep track of where the stack top is, right? So we don't actually have to use a standard stack, like a standard queue or some shit or vector, and push and pop stuff off of it, which is super inefficient for other reasons like memory and reallocation and things like that. But we basically end up only moving a number, and with that we know where the index into the stack is, where we do actually have the top without having to reallocate at any point. Pretty fucking basic. I don't know why I'm explaining this. I don't expect toddlers to be watching here, but yeah. Then we have the program, which just has a program counter, and the stream of instructions, which is just a vector. Okay, so a vector of instructions. Okay, so it's pretty basic, and then the instruction itself is. It's been a while since I wrote this, so we will need to look at this right now so that I get an idea of what I'm supposed to be writing without having to reinvent everything. And then in the instructions, we have an operand, an opcode, and the value, which is 56 bits worth of value. Makes sense, right? 64 bits for a whole instruction. Then you have 8 bits opcode, or is it 8 bits? That seems wrong. No, yeah, no, it's 8 bits. Yeah, if you can do some math. And then 56 bits is the actual value. Pretty simple. Right. Okay. So there's a bunch of stuff here that we might not need, but we'll see. I mean, there's a union, which is, terrible. But yeah. Now, these are all the instructions that exist, and we're going to look at the, let's look at the actual implementation of the interpreter really quick. And if you don't understand any of this, it's fine. I'm going to get into exactly how this works later when we go into the implementation. I'm just looking at this really quick to mostly refresh my memory on this, but it might be interesting. So we have push instructions and pop instructions, of course. So push is just pushing into the stack. The error check here doesn't matter. But basically we just write into the stack at the position of stack top and then move the stack top by 1. And then the pop instruction is going to be the same thing. Pretty simple. And pop ignore just pops without giving us the value back. Pretty nice. I'm going to use my mouse here. Sorry, if you're Vim Pro, look away for a second. Swap is just literally standard swaps, the stack top plus 1 and plus the other offset. And then we have some other instructions here, but they're all implemented like this, right? There's no JIT, which is just in-time compilation here. We don't generate any machine code instructions based on the instructions in the bytecode. And we also obviously don't have any semantic optimization here, which means, for example, in Java, the GraalVM will take the abstract syntax tree of the program. I think it reconstructs it from the bytecode. I don't actually know. I didn't look into it that much. But what it does is basically then take that AST, that abstract syntax tree, which basically just represents the entire program in a tree structure, if you will, and can then optimize it by walking the tree, rearranging it, and taking parts of it and optimizing it into bytecode, into JIT compiled machine code, which is really smart. We're not doing any of that right now because why would we? And then we have execute function, pretty simple. This is just a switch case. There is a wonderful optimization you can do here. That is a computed go-to label thing, where you basically, instead of doing a switch case, you generate a large array of your code, basically, and then you use goto to jump to that code in the array. So these add, inc, and so on, these are instructions that have values, right? So they are like 0, 1, 2, 3, and so on. And you use those as an index into an array, and you just jump to those immediately by using the the goto keyword in C++, which translates roughly to a jump instruction in assembly. So what happens is that you skip the whole branch prediction bullshit of switch case statements, which if you optimize if you profile this specific code, which I've done, of course, is actually a huge time loss. Like most of the optimization you can do here is improving the switch case to basically just know where to go instead of having to fucking guess, okay? So that's the point of what you can optimize here. I don't know why I'm talking about this, it's completely irrelevant. There's a few special instructions that like dupe2, there's a few more, let's go to the instructions. This is actually interesting, so stick around. There is, I think dupe2 is the big one, where if you have two dupe instructions, it will replace it with a dupe2, things like that. Yeah, so there's a few instructions you're not supposed to use, and the compiler will just detect when you're basically doing the equivalent. So we do a little bit of optimization here, but it's not a lot. It does have a significant performance gain in some programs, like the Primes program, but yeah, so I've been talking for a solid 15 minutes about this shit. So we're going to get into setting up the Rust project really quick, and then we're going to call it a day, I think, for today. And then next time we're going to actually implement most of this. That sounds good to me. Does it? It does. Okay, so we're going to make a new Rust project. This is the cargo.yaml. I'm just calling it MCLRS to really go with the meme of having it be a rewrite. Cool. Okay, so we're gonna add some dependencies like clap, and I think that's it right now. I think. Oh, is it nvlogger or what is it? Oh shit, sorry. Yeah, nvlogger, and we want vlogger, I think. Do we care? I don't know, we'll see. Okay, and we're gonna start with implementing this. So the first thing we need is to parse some command line arguments. Well, we don't necessarily need to start with that, but I like starting with that. So it's like the interface of the program. It's nice to start with that to figure out what you actually need, how you're gonna structure it. So the first thing here is gonna be a class use parser. Okay. And then what we're gonna do is struct parse. So we're gonna have compile exec is optimize, I think, and there is decompile, right? It can also decompile code. Let's show that actually really quick. So MCL decompile samples primes MCLB, and what it basically does is it generates random words. These are not real words. It just generates them based on some basic like consonant vowel type thing, and then just builds all these instructions. So yeah, it does a decompilation. Kind of nice. Kind of good to have. If you don't build it, someone else will. But oh yeah, there's some instructions as well, like jump 0 jump equals, and stuff that it might figure out as an optimization step. Doesn't matter. We'll figure it out later. Okay. We're not going to implement all of these right now, but we'll see. We see how it goes. You can ignore the error probably. So I've actually been writing some Go recently, so if you see me writing this shit, that's why. So wait, does parse fail? Let's run this really quick and see what happens. Also, don't come at me with your workflow. Like, I know my workflow is terrible. Um, how do you do this? Let me check this really quick. Let me look up how you do clap. Let me quickly show you, actually. Might as well, right? There we go. Okay, so this is clap. Sorry for the fucking spook. There you go. Arg. Oh, default value, that's the one. Okay. Yeah, we want default value to each to make sure that we actually don't have to provide this, because I'm not going to provide this every time. So arg default value t true. So true, 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 false. Let's try that. Positional, but must take a value. Must take a value. How about we do specify that these have to be long options? But yeah, if this doesn't work, I'm just gonna do it later. I don't really care too much about it. Yep, worked fine. Okay, that was the problem. I was missing the thing. So now what we should be able to do is run it with dash dash help, and it'll give us all these options, and we'll fill out later what they actually do. But I think that's gonna be it. Let's see what else we need to do. Also, my music went away. That's horrible. I'm sitting in silence like a fucking goofball. Oh well. Oh, got flashbang. Okay, so if ours, oh, wait, is it? Another one I want to use anyhow. All right. Okay, it doesn't let me, but I know that this is the thing. So if args.compile, we're going to compile it. Now let's figure out if we want to have like a compiler sort of module. I think we do. I think we do. Compiler.rs. Okay, so compiler.rs is gonna have let's do that. Compile, and then what we give it is probably bytes, right? So string content. I'm just gonna do that, and it gives us back a stream of the bytecode stream, right? Because we don't actually want to have to write it to a file. We want to avoid any sort of side effects, so we can unit test it. So I'm guessing I'm gonna write it to a back U8. Maybe. I mean, I think this would make sense, right? Well, I mean, technically it's U64 because it doesn't particularly matter. We can probably skip the whole. No, let's do like this. Okay, so compile is going to do this. It's going to be anyhow result. I'm using anyhow because I can't be bothered to figure out which errors are which right now. We can replace them later if we actually want to use proper error handling and shit. Right now we don't. So let's figure this out. So if ours compiled, then we're going to do bytecode vect. Yeah, okay, it's gonna be empty, right? And then what we're gonna do. Oh, fuck off, dude. Do we care? No, I don't think we care. I think it will figure it out. Bytecode is compiler compile, and then we need content. So right now, let's just do this, and we don't really particularly have to care. There we go. Okay. So and then if args exec, then we want to do bytecode. No, interpreter, execute, bytecode. Okay, so this is what I'm thinking, right? This should allow us to encapsulate them both properly. Interpreter dot rs. Come on. Oh my fucking god. Did that work? I don't know. Cloud function execute. Okay. So execute's gonna take that bytecode that we talked about. U64. Do we care? Let's move it. Fuck it. And it's gonna return a result. And we don't really need to we don't really need to do that. Oh, actually, we should keep track of a VM state, right? So maybe we want to do struct VM. Just call it a VM because we can. And we're going to keep track of the bytecode and the stack and things like that. So let's do that here. So stack bytecode back U64. Actually, we probably want to. No, that's great. That's correct. And then this is supposed to be pop. Come on, get real. So we're gonna go self backups. Okay. All right, and then the stack is gonna be just the same. I think we can just use a vec here because we don't particularly care what it is, and yeah, we don't care what it is. So we're gonna abstract this away anyway. So data, no, fuck, back U60. Well, it's I64 in this case. Okay, that's the stack because it holds I64 values. Now, of course, we can immediately start doing a value type. Ooh, I'm tired today. Okay, integer 64, and we can later add other types to this, which lets us implement floating point strings, that sort of thing that we wanted to do. I think that's going to be fun. So right now we're not going to care, of course, but okay, so execute is going to take the bytecode and run it. So what we're going to basically do is switch over the bytecode. Oh, it's called a match. Match the bytecode, and we probably want to decode it right here actually. So we want to say the bytecode and was it 8 right shifted by 56 bits or some fucking shit like that. Actually, yeah, let's do that. Why not? No. Okay, so right shift by 56 would mean that it is the 8 bytes on the very left, which is the opcode. And let's actually look at the specification really quick just to be sure, but I'm almost at the 30-minute mark, which is where I do want to call it. So let's not go crazy here, but where's the fucking... There it is. Wonderful. Great. The reference. Okay, so the MCL reference tells you how exactly works. Okay, so the bytecode is 2 bytes. No, 1 byte instruction. Yeah, 8 bits. Yeah, 1 byte. That's correct. Okay, 7 bytes value. Yeah, sounds good. Okay, so maybe we want to actually extract this then. Oh my god, I have too much shit open. We want to probably extract that then, and call it a day. So let's do that. Let up is Dutch, first of all. Shout out. But also it's bytecode and 8 right shifted by 60 minus 8. It's a little bit easier to see, I think, where that is coming from. The value is bytecode and actually, you know what? Let's do it. Let's do it an easier way. So React, so that's 8, right? 2, 4, 6, 8. Yeah. How do you do that in Rust? Like this? Okay. So we want to actually have yeah, so this is the entire value, right? And then what we want to do is have this byte. And then in this one, we want to have these bytes. And of course, if you AND bitwise AND, if you bitwise AND something with 0xFF, then that byte stays what it is. If you AND it with 0, it disappears. Okay. So and these we obviously have to also right shift by 56. So 64 minus 8. Okay. And these we don't have to right shift. Right, so this should yield an opcode. And as I said, we can optimize this later. Oh, we want to do this in a loop, of course. So this is, wow, brain fart, what the fuck? For byte and byte. It's not byte. It's not byte. It's a stupid way to call it. Let's call it a instruction. Raw instruction. Okay, so we're gonna match up, and if it's something we don't know, we're gonna return error. I don't know, something. We'll figure this one out later, actually. Right now, let's just panic. As I said, we're actually gonna do this later, but like, and now if is the instruction for push, which is 1, I believe. We're gonna push. Okay, so we're gonna do 2 things. We're gonna do print line push, we're gonna do value, okay? And then we're gonna actually push it, but we're gonna do that later. So right now, all I want to do, okay, is have the compiler do one thing and then the other one do one thing. So right now we're gonna ignore the compiler and just have the interpreter. And oh, this might take a little minute. Okay, the stack is gonna be a stack with capacity yeah. We'll resize this. It doesn't matter right now. Resize it later. Okay, so the bytecode is then empty vector, right? Okay, so now in the main we should be able to say make a new one and then vm.execute. And the bytecode itself is going to be if we don't provide it right now, we're just gonna do back. Whoa, whoa, what the fuck? All right. It's gonna be 0x01 followed by like 1. Well, actually 0x01 right shifted by 56. All right. That should be all we need, and then we should be able to just do cargo run exec. All right, go down compile because of the absolutely horrendous result thing that we did in the compile. We don't care right now. And it did not actually run up. Cringe. Well, but we got some basic infrastructure up and running for this to work. Full raw instruction in bytecode. Raw instruction and that. Yeah, weird. That should have worked. I feel like maybe this doesn't work because, well, actually, this never runs, does it? Does this run? I can't tell. Exec. Weird. Let's do a fun thing. Let's actually debug this really quick. And then oh shit, sorry. Fuck off. Okay. Exec. Oh, actually, let's break at main and then exec. So yeah, okay, so when do we get to my code? Okay, doesn't matter. Break at main.rs. Source main.rs. I don't know how to do this. Line 19. Yes, that worked. It's great. It's crazy. Just like that. Just like that. Exciting, really exciting. We parse. Oh my god. I fucked up. Alright, let's do it again. Next. I've been writing too much assembly now. I just always type S when I want to type N. So bytecode is length 1. Oh, fuck off. Okay. Cool. Next. Oh, it compiles it. I'm stupid. So let's just disable this for now. Sorry, that was fucking stupid. Okay, so push 0. It's not quite right, but we did detect. Oh, actually, no, it is right. It's right. It's exactly right. Yeah. So effectively, we now have an interpreter that can run our code, our bytecode, right? And this is the most basic bytecode in the world, but that's the whole point of this educational, right? So we've written this part, and the compiler is completely not existent yet. But we can actually start with the interpreter because we can use bytecode emitted by the old compiler if we want to, because the compiler itself is kind of boring. So we might do that and just set it to be disabled by default and just use the other compiler for now. But yeah, hope that was interesting. If not, let me know, because then I don't have to waste my time doing this. But right now it's fun, so why not? Thank you for watching, and I'll see you in the next one where we're going to actually build most of this shit. Yep, sounds good. See you next time.